Hi, I'm Zor. Welcome to Unizor Education. Today we will talk about limits of multivariable functions. This lecture is part of the course called Math4Teens, presented on Unizor.com. I do suggest you to watch this lecture and all other lectures of all other courses on the website. You might find it on YouTube, let's say, but you'll just find one singular lecture on Unizor.com. The courses are presented in some logical sequence, with menus, with problem solving, with exams which you can take, and everything is totally free. There are no advertisements. You don't have to sign in if you don't want to. So I do suggest you to use the Unizor.com for this. And besides this particular course, which is called Math4Teens, there are others like Physics for Teens, Math Plus for all, basically, Physics Plus, Relativity. Okay, so let's get to business. Multivariable functions. Now, the limits for multivariable functions is kind of tricky because if you will take some function, let's say f of 3 arguments, for example, doesn't really matter, and then each one of them goes to certain limits, what will be the limit of the function? Well, it depends how they go to their limits. I mean, there are different trajectories from some point in the space x, y, z to a point with coordinates a, b, and c. You can go this way, you can go that way, and depending on the way you go, you might have different results and different limits. So our purpose is to establish certain conditions when this limit does exist. Well, let me just give you an example. If you have a function arctangent x plus 2 to the power minus y plus z over z plus 1. Now, if all of these x, y, and z go to, let's say, plus infinity, what happens? Well, arctangents by itself, if you go to infinity, it will go to pi over 2. Now this minus y, so it's minus infinity, this goes to 0. And z over z plus 1, if z goes to infinity, that would be 1. Okay. Now, it looks like the limit of this thing would be p over 2 plus 1. But is it important how we check this particular thing? Well, the way to do it is, okay, let's just fix x and y and do only by z. So what will be the result? Result would be the function which is arctangents y plus 2 to the minus y plus, and if z goes to infinity, would be 1. So we start from z. Now let's say fix y and do only the x. What happens? Well, the function would be pi over 2, because the limit of arctangents of x, if x goes to infinity, is pi over 2, plus 2 to the minus y plus 1. And finally we go by y. So if y goes to infinity, this goes to 0, and the result will be the same. Now, if you will do in a different sequence, it will be still the same. But let's consider a different function. This is a function of 2 arguments, x over y. Let's say we fix y. So we consider the function with x goes to, let's say it's x and y goes to 0. So if x goes to 0, then the function would be 0 over y. And this is 0. So now, no matter how y is changing, the result would be 0 because it's already constant. So the limit of this function, if we start from x going to 0, limit would be 0. But what if we start from making limit, if we will just do not touch x and put y to 0, well, it would be to infinity. And actually it depends which infinity, plus or minus, which means there is no limit, basically. So if you will start by moving y to 0, not touching x, fixing x, then there will be no limit. So it's already a difference. This is 0 if we start from x, and if we start from y, limit would be non-existent. So there are tricky situations here. And again, our purpose is to establish when the limit would exist actually, regardless of the sequence of making one argument going to whatever the limit is, not touching other arguments. Okay, fine. So now let's recall a concept which we have introduced for sequences. And the name of this particular property of convergence was uniform convergence. Uniform convergence. It did help us with double limits for sequences when there are two indices involved. And it will help us in this particular case as well. So for simplicity, let's just consider one particular kind of multivariable function, only of two arguments. If it's 3 or 4 or whatever, it doesn't really make any change, except it's a little bit more tedious. So I will consider the function of two arguments, and I will introduce this concept. Basically, the concept is that, so let's say we have some kind of a graph in two-dimensional case. So this is a surface, basically. These are x and y. And we are talking about x and y going to specific points. What would be the function? So if, let's say, we will go only by x and we will not touch y. So y will be here, and this is x. So trajectory would be something like this. That would be the result. Now, if we will go by y to this particular thing and do not touch x, then it might be something like this. And we will go to the same point. So this point would be the limit if x goes to, this is, let's say, a, and this is b. So this might be f of x b as x goes to a and y goes to b. Okay. Now, what uniform convergence actually means? It means that whenever we are moving, let's say, by x, then after a certain amount of time, we will be in the neighborhood of this point. Okay? Now, we will be in the neighborhood of this point, but the problem is that y can be different, can be here, can be there. Y is not actually going to a limit. Y can be anything. So what we are looking for, that within certain neighborhood of this particular limit point, where x is equal to a and y is equal to b, we don't really fix y. So x goes to this particular point, but for any kind of a y within this category, the result would be that the function would be very, very close to this particular value. Now, let me do it in a little bit more mathematical way. So we are looking for the following property. If we choose any epsilon greater than 0, neighborhood basically, of this particular function, and it means that we will find that would exist. So x goes to a. Okay? Well, it means that x gets closer and closer. So x would be there exists such, let's say, delta 1 that exists delta 1 that if x is very close to its limit point, as x goes this way, closer and closer, the function, obviously f of xy, would be closer and closer to f of a y, right? If the function is continuous or whatever, but in any case, it will be close to the limit. Let's put it a limit. It will be close to the limit of f of xy as x goes to a. Let's call this function y of y, because we are not fixing, x goes to, but we are not touching y. So as x goes to a, this function goes to this limit, and limit would obviously depend on y. But with uniform dependency, uniform convergence means that if y is also sufficiently close, let's say less than delta 2, to its value, so x goes to this way, but then y is somewhere within this particular small area, less than delta 1. So exist delta 1 and delta 2. Then the function of x and y would be different from y of y, lowercase y less than epsilon. So again, for any y within certain neighborhood of its value, so which means we are restricting ourselves for this one and for this one. So it's some kind of a rectangle here. So if we are within this rectangle, then the value of the function would not be deviating from this particular y of y, which is this limit, by greater than epsilon. So that means we are uniform by y. As x goes to a, we are uniform by y in the neighborhood of its limit point, neighborhood of b. Similarly, we can say that the function is uniformly convergent by x is y goes to its own limit. Let's say if y is less than b by, let's say, delta 3, so exists delta 3 and delta 4. If y is in this neighborhood and x is also in this neighborhood, very small one, then limit of f of xy by y goes to a, which is some kind of function x of lowercase x, then the difference between them, so x of x minus f of xy, would be less than, again, less than epsilon. So for any epsilon, the uniformity, uniform convergence by y, if x goes to its limit, is basically closeness between this function and this limit by x goes to a would be less than this epsilon. So there will be a neighborhood where this is satisfied. Same thing, opposite. If y goes to b, and we are talking about uniformity by x in this particular case, so for any x, that would be the true function. For any x within certain neighborhood. Now, if we will talk about delta 1, delta 2, delta 3, delta 4, obviously we can have the smallest delta. So for any epsilon, if exists delta 1, 2, 3, and 4, we can have the smallest of them, and then everything will be satisfied. So as long as f of x y is uniformly converging by x and by y, so by x if y goes to b, and by y if x goes to a, then, and now we are talking about going to a limit, then we can have very simple logic, which I will basically express as a theorem. Okay, here is the theorem. Well, we have function f of xy, and we would like to know what happens if x goes to a and y goes to b. So what's given? Given is the following. Let's go only by x and y be as it is, basically. So limit of f of x y, if x goes to a, is some kind of a function y of y uniformly by y. What does it mean? It means that the difference between f of x y minus y at y is less than that particular epsilon, whatever the epsilon we choose, and within certain small neighborhood around xy, around AB, xy around AB. Now let's say limit of ya of y as y goes to b is, well, let's say it's b. Now this is the normal, so this is a function, the limit of function of two arguments, if one goes to certain value, is a function of another argument, right? Depending of y, that would be different value. Now, but this now is a function of y, and we have a normal point related convergence. So this is normal. There's no such thing as uniformity in this particular case. Now, let's do it in reverse. What if we will do first limit of f of xy by y goes to b? Now, if y goes to b, then it would be function of x. So it's x of x uniformly by x. I should say lowercase. Now the regular limit. Then a must be equal to b. So no matter which order, first we go with this function by x to going to a, we'll get the function, and then go with this function by y going to b. We have some resulting. But now if we will change the order of limits, first we will do the limit by y, getting function of x, and then from that we go to x goes to a, and we get another value. So this value must be the same. Again, most important condition is uniformity. Okay? Now, how can I prove it? Well, very simple. I hope this would be enough for me. Let's say a is not equal to b, and difference between them is d, which is greater than 0. Okay? Okay. I will basically come to some kind of contradiction which will prove that a is supposed to be equal to b. So how can I come up with this contradiction? I'll choose epsilon equals d over 4. By the way, this is very much close to the similar proof which I did for sequences, for double limits. Okay, so let's say epsilon is equal to d over 4. Now, since this is uniformity, then for this particular epsilon, there is some delta such that if x minus a is less than delta and y minus minus b, so we are in the neighborhood of their limit points, follows that f of x, y minus, in this case I will use this one, y of y less than epsilon. Now I choose the same delta here and delta there because obviously I can have delta 1 for this and delta 2 for this, and then I will have a minimum of delta 1 and delta 2, which means both of them satisfied. So that's why I choose the square instead of rectangle around limit point a and b. Okay, now that's from here. Now let's go with the second one. The second one gives me that for the same epsilon, there is again another delta 3 or whatever you want, but then you will have a minimum of 4 delta. So we can say that for y minus b less than delta, we will have this one. Y of y minus b is less than epsilon. So this is from this. So as soon as y is closer to its limit point b, capital Y of lowercase y would be very close to its limit. That's what limit actually is, right? That's the definition from the limit. Now compare this and this. So this value is a number minus this would be less than epsilon, and the same y of b is also less than epsilon. What does it mean? Well, it means that f of xy minus b is supposed to be less than 2 epsilon, right? Distance between this is epsilon, distance between this is also less than epsilon, which means the distance between this and this should be less than 2 epsilon. Okay? Great. Well, as long as x and y are in some very close neighborhood of their points, limit points. Now, let's do exactly the same, but start from the x. What do we have? Again, we choose the same epsilon. There is such a delta that if this is x and y are within certain small neighborhood of limit point f at b, this would be an inequality which I'm looking for from this. Since it's uniformly, then the difference between them would be less than, regardless of x, for any x actually within this particular neighborhood. And from this one, we will get again similarly, if x is within this neighborhood, then difference between function capital X of lowercase x minus a minus its limit points should be less than epsilon. And again, this from this is distance less than epsilon, this from a is less than epsilon, so from f of xy to a would be also less than 2 epsilon. Okay, now what is 2 epsilon? 2 epsilon is d over 2, right? Epsilon is d over 4, so 2 epsilon is d over 2. where D is the difference between A and B. Now, if this is a difference between A and B, this is half. So this value should be closer. This is f of x, y. It should be closer, less than D over 2 to the B, and it should be closer, less than 2 over 2 to the A on both sides, which is impossible, right, if the whole distance is D. And that's the contradiction we are looking for. And that's why A is supposed to be equal to D. Which means no matter how we will calculate the limit, we do not touch, for example, first we do not touch y and go by x to a limit, and then the resulting function, then we will choose y going to its limit. That would be the value. Or we will do vice versa. We don't touch x and do only y goes to a limit, and we will get some kind of function of x. And then we do the limit by x, we get another value, and that value must be exactly the same if uniformity is satisfied. And in whatever example I did before, when the limit does not exist, there was no uniformity, obviously. Well, that's it. So what I suggest you to do is go to this website, go to Math4Teens course. That's the limit of, go to calculus, limit of functions. That's the big chapter. And in that chapter there is a lecture called Multivariable Limits. And just read the notes to this lecture, because every lecture has a note, and it's like part of the textbook. And that would be very, very beneficial. I do suggest it, because I do it a little bit maybe smoother in the text, because I was just thinking about every word, and here it might be a little chaotic or whatever. I hope not. So enjoy it, and thank you very much for your attention.